Hi everyone, I'm Helen. I use ice core records to look at the record of past volcanism, and I've been working on a project looking at the Los Chocoyos supereruption, trying to find it in the ice cores. So Los Chocoyos is an eruption from the Atlantic crater in Guatemala, part of the Central American volcanic arc system. It's thought to be one of the largest eruptions of the last 100,000 years, estimated from the vast quantities of tephra that have been deposited all across the region, creating the largest quaternary tephra horizon in Central America. Because it's such a large eruption, it's anticipated that there were decades of cooling following the eruption due to the amount of sulfur dioxide that was released to the upper atmosphere. In terms of the age of the eruption, until recently, an age of 84,000 years has been accepted, from a sediment stratigraphy study that was done in the 1980s. However, a recent study using zircon rim ages has suggested this eruption is significantly younger than previously thought, about 75,000 years old. This is interesting, as it's been pointed out, it's within dating uncertainty of another supereruption, the younger Toba Tuff, and that therefore brings up questions about what a potential double supereruption might have caused in terms of impacts to the climate. These eruptions are of particular interest because of their proximity to a major climatic transition into a cold period known as Greenland Stadial 20. We can see these warm and cold periods in Earth's history by looking at climate temperature proxies, and that's what we have here is oxygen isotope record from ice cores. This shows the warm and cold periods with the more positive values representing the warm periods and then the more negative values representing the cold periods. Because both of these eruptions occur here, it brings into question whether these extremely large volcanic events actually trigger or whether they exacerbate the effects of these millennial scale cooling events. Ice cores come in because we have a very well resolved age model in ice cores, and this allows us to more accurately date the eruptions, but we can also use the deposits in ice cores to understand more about the eruption characteristics. We see volcanic eruptions in ice cores as these large aerosol peaks, in this case sulfate aerosol, which is often accompanied by volcanic ash that has also been transported potentially from equatorial regions to the poles. The ash is key in determining a source of the eruption that we see in the ice cores, and this is because of the unique geochemistry of the tephra that can be matched to the chemistry of the volcanic source. And this is currently the only way that we can tie a source to an ice core deposit. When we look more closely at these ice core deposits, we expect the tephra, because of its larger particle size in the aerosol, to fall out immediately prior to or during the growth stage of the sulfate deposit. So we expect to see it somewhere here, as this figure shows, just in the upswing of the sulfate deposit. For this particular project, we targeted 3 different ice cores to look for the Los Chocoyos eruption. We have 2 cores from Greenland, the Northrop and Neem core, and 1 core from Antarctica, the EDC core. Because we have such a large deposit in both poles at the same time, it suggests it's from a tropical source. And the size of the peak is also characteristic of an extremely large eruption, and therefore a prime candidate for Los Chocoyos. We wanted to do this study at extremely high resolution, so we took each section of ice containing that aerosol peak and subdivided it into much smaller samples, so we could see how that sulfate evolved through time. And we also looked at each individual sample for the presence of tephra, so that we could determine, relative to the sulfate peak, exactly where it was occurring. These are the sulfur profiles from the Neem core in Greenland and the EDC core in Antarctica. And you can see that in both these ice cores, we have multiple samples that contain tephra. Because of the settling of tephra relative to sulfate, we are most interested in samples here. So just on the growth side of the largest sulfate peak in each of the sample sets. Because Los Chocoyos was our candidate eruption for the ice core deposit that we see, we analysed the major geochemistry of samples that are proximal to the eruption site. And we found that our own major oxide analysis using electron probe microanalysis was similar to what is in publications. So this is good, this means our method was working. This acts as a reference value that we can compare all of our ice core tephra to. And when we compared the shards that we'd analysed from the ice core, we found we had 6 that correlated really nicely with all major oxides of the Los Chocoyos geochemistry. 2 of these shards are in Antarctica and 4 of these shards are in Greenland. So this is the best evidence we have to date in the ice cores of Los Chocoyos. Because we did the study at high resolution, we can see in exactly which samples this ash has been deposited. And in both cases, they are where we would expect in that kind of area, right as the sulfate peak's growing in. What's interesting is in the Greenland core, so in the Name core, we actually have 2 distinct deposits of the ash separated by an interval of about 16 years, which we can see at this resolution in the ice cores. Not only are these separated in time, but interestingly, they also have slightly different geochemistries. So the first deposit comprises of 1 shard, which is this one here. And then 16 years later, we have the remaining 3 shards being deposited, which seem to have marginally lower silicon and marginally higher iron concentrations. What's fascinating about this is if we actually look at proximal Los Chocoyos ash geochemistry, which has been done through a stratigraphic section, we see that this reflects what we see in the ice cores, with the initial ashfall deposit having marginally higher silicon and lower iron compared to the later units, later Ickenbright units, which especially towards the top here have lower silicon and higher iron, which, as I said, is reflected in what we see in the ice cores. So although we have an extremely small data set in the ice cores, the fact that we have the separation in time potentially suggests that instead of being one colossal eruption, Los Chocoyos might have consisted of multiple pulses of eruption instead. And this particular study kind of shows how ice cores can therefore benefit us, seeing things because of the continuous deposition of ice cores that we might not necessarily be able to pick up on in proximal deposits. Because we found tephra in the ice cores, we can determine an ice core age for Los Chocoyos of 79,500 years. But how does this fit into our previous dates that I mentioned, the sediment stratigraphy age and the radioisotopic age? The ice core age is kind of in the middle of these 2. It doesn't necessarily agree with either. But because the sediment stratigraphy age was determined using age models created in the 1980s, we thought we might revisit it and see if we could improve. So the study that was originally done for the sediment age model used this core down here, B1929. It's about 2,000 kilometres from the Los Chocoyos eruption site, and it contained a 2 centimetre ash horizon geochemically correlated with Los Chocoyos. When we investigated other sediment cores in the area, we found that actually right next door to this core was another one, B1930, which has a much higher resolution benthic oxygen isotope record that these age models are based on. We looked for the Los Chocoyos ash and we managed to find it and geochemically verify it in a section. And this is the depth that we found it at. So on this age model, we found that the Los Chocoyos sediment age in B1930 was at a position that made it 79,300 years old. If we adopt this as the new sediment stratigraphy age for Los Chocoyos, we see that's actually in very nice agreement with our ice core age. So finally, we thought we'd look at this radioisotopic age that was done. The study that determined this used uranium, thorium, helium ages from zircon rims, and that's what this data set here shows. Interestingly, you can see the ages that were calculated, but also the uncertainty bars associated with them. The uncertainty bars for the younger ages are much smaller compared to the older ones. We found that if you calculate a weighted mean using the absolute uncertainties of this data, it's going to bias it towards the younger ages. We thought we'd try recalculating it, but instead take into account this difference in uncertainties of the younger and older ages calculated by zircons. And when we did this, we found an age that was perhaps more representative of the data set and instead was 78,700 years. This agrees beautifully with our other 2 ages, yeah, this is great. It agrees perfectly with our other 2 ages and kind of brings together nicely, verifies our ice core age. So what are the implications of this ice core age of Los Chocoyos? If we adopt it as being about 79,500 years, we can first of all rule out the possibility that there was a double supereruption between the Los Chocoyos supereruption and the younger Ptah. This is especially evident when we look at ice core sulfate continuous data, showing the volcanic peaks. So we see that Los Chocoyos here, the peaks that we've identified, are several thousand years before the TOBA candidates over here. In terms of the climate, we can again look at that temperature proxy, seeing when these warm and cold periods are. And the age of Los Chocoyos here at 79,500 years is actually in an extremely stable period during Earth's climate history, and definitely well away from this transition into Greenland Stadial 20 here. We can therefore rule out Los Chocoyos as a driver of these millennial scale climate changes. However, the vast quantity of sulfur that's released from Los Chocoyos, and we've calculated the sulfur flux to the stratosphere using the ice core data as 192 teragrams of sulfur, is consistent with eruptions that would likely have several years, potentially a decade of cooling associated with them. So that's what we've learned about Los Chocoyos from the ice cores. We've learned that it's possibly more an age of 79,500 years, and we've backed this up by revising both the sediment age and revisiting the radioisotopic ages that have been published. This allows us to determine that Los Chocoyos was not a driver of the millennial scale cooling, but the ice cores themselves lend to better understanding of eruption behaviour, potentially being able to show us if there are multiple pulses of eruptions going through history. So, thank you.